Can you see my slides?
Yes, sir.
Okay, let's wait for another 30 seconds.
Sir, you are not audible, sir.
Oh yeah, thanks. All right, anyway, let's get started. So we'll discuss today the atomic structure, say in a very simple way. We won't go into complexities because we don't need it for this course, the complexity part. But we need to understand how the atoms are aligned inside the crystal, in a typical crystal, because we are talking about growing crystals, right? Small crystals, which we are calling as nanoparticles or some other forms of nanostructures. So many varieties are there. So like nanowires or nanosheets. Okay. So the properties depend a lot on how the atoms are aligned. Okay. Now, when we're talking about a nanomaterial, say as an example, we're talking about gold or silver or zinc oxide, zinc sulfide, all right, copper oxide, cadmium selenide. So many different types of nanostructures we're talking about. And we also discussed before, if you remember, that the lattice parameters change as the material becomes small. Otherwise, the crystal structure is the same. All right. So the crystal structure of gold or the crystal structure of zinc oxide or zinc sulfide is the same if you talk about a bulk material or a nanomaterial. The difference is that because of the size, there is a tendency for the atoms to reduce the space between them, okay, between adjacent atoms, and that is what we call as the lattice parameters, right? The lattice spacing. The word lattice basically means the arrangement of the atoms, okay, because like I told you, the atoms have specific places where they can sit. So it's like a unseen geometric structure, okay, if you visualize, right? The atoms are there. It's not like there are lines connecting the atoms, but the bonds, basically those are the bonds. So in a pictorial representation, we draw it like some geometrical figure, like a cube maybe. So these spacings between the atoms, they slightly reduce at the nano scale. Otherwise, they are the same. Okay. So let me go to the next slide. Three terms that we need to remember. Unit cell, I mentioned a number of times before, and let me repeat it again. If we cut a crystal smaller and smaller and smaller and smaller, it will have repetitions. I mean, it looks exactly the same. Finally, we go to a state that this is the minimum size. That means if we cut it down further, it won't replicate. It won't be looking the same. That means in a typical crystal, the unit cell is replicated in 3 dimensions, okay, to get the complete crystal. Okay, so if you have to define that, we say is an irreducible, okay, cannot be reduced further, representation of the crystal structure, okay, of a pure material defined by a set of parameters called the lattice parameters. So what are these lattice parameters that explain it? These are the length units and the angular units. Okay, so if you look here, you have the length units there along the x, y, and z axis as A, B, and C. Okay, and the angles here, alpha, beta, and gamma. Right? So this is a simple cubic one. So all the angles here, alpha, beta, and gamma are all 90 degrees, but these may be different also, right? Based on what type of crystal we are talking about. This is a simple cubic structure. So here A, B, and C all are same, and alpha, beta, and gamma are same, all right, 90 degrees. But this is a very, very basic representation. Okay, there may be complex crystal structures or unit cells. Okay, we'll come to a few of them. So the lattice parameters include the cell dimensions A, B, and C, and the crystallographic angles alpha, beta, and gamma. Okay, so basically these 6 values tell us a lot about the shape of the crystal structure and the spacing between the atoms. Then we talk about a number which is called the coordination number. So this is basically referring to the nearest neighbors, how many nearest neighbors a particular atom has within the unit cell. Okay, nearest neighbors means they are bonded neighbors. Okay, they have bonds between them. Okay, so if you look here, this atom is bonded to this one, bonded to this one, bonded to this one, right? But it is not bonded to this one. Correct? There is no bond connecting these. So if you look here, we'll say 1, 2, and 3, but this is a unit cell. Okay, so this one will have 3 nearest neighbors. Okay, so that is a coordination number. Packing fraction is the fraction of space occupied by atoms within a unit cell. Okay, how much amount of volume is occupied by atoms physically to the total volume of the unit cell. That means if I divide the volume occupied by the atoms inside the unit cell to the total volume of the unit cell, I'm going to get what is called as the packing fraction. Okay, so lattice constants are characteristics of the unit cell that define its volume with the dimensions and the angles between them with the angular lattice parameters. So this is a very simple structure, but these are other examples which are not so simple as you can see them. Okay, so this structure is called rock salt, this is zinc blende, and this is wurtzite. Okay, so wurtzite is very typical of zinc oxide and zinc sulfide, and zinc blende, that's another variation where zinc sulfide is also available in this form. That means the same material can be available in 2 or 3 different forms or 2 or 3 different crystal structures. Okay, so let's discuss a little bit just to get a proper visualization of what we are talking about. Let's start with a very, very simple crystal structure. We call it the simple cubic crystal structure. Okay, so it is basically a cube of equal sides, right? And that means A, B, and C, A, B, C are all same, and alpha, beta, and gamma are also same and they are 90 degrees. Okay, so that is basically what it means is that this is how the atoms are aligned. These are the atoms sitting in the unit cell. So if I have to build up the whole crystal, this unit cell will be repeated in 3 dimensions. Here also, up also, bottom also, this side also, outside the screen. All right, it will be translated in all directions. Right now, here we are showing the atoms are very small. The unit cell is quite big. But what we are talking of when we say about packing fraction is that we forcefully try to force them in as much as possible. All right. So you see here now, this is the situation. We have forced the atoms in. These are the 4 atoms in the corners. Okay. That means if I connect the center of all these spheres, I am getting this unit cell. Right. But this is what we call as a tightly packed unit cell. That means all the atoms are touching each other as much as possible. It cannot go further in, cannot be packed further in. Okay, so this is the situation. Now if I cut out the unit cell from here, this is what it will look like, because only a part of the atom will be inside the unit cell. Like I told you, the unit cell is drawn from the center point of the sphere. Okay, the centroid we call it, right? The centroid of the sphere. All the centroids, if we connect, we are getting this type of a unit cell. And then if we cut out the unit cell, this is how it looks like. This is a fraction of the atom which is inside the unit cell. Now if you typically look at it now, can you tell me what fraction is this of this one? I mean, how many parts of this, if I cut it out, will be inside? So you think about this now. One particular atom, if you think about the centroid now, so from the centroid we are cutting out, and we will have, this is just one unit cell, we'll have another unit cell this side, correct? Another unit cell on the top, correct? Another unit cell here. So ultimately, one atom is basically connected to 8 unit cells, right? Think about it, because we are cutting the sphere into 8 parts. Oh, no. মই যাম আজি অফিচ আজিতো ৰঙাখন নিব লাগিব এখন ৰেডি কৰি দিব কোৱা ক্লাছ আছে এতিয়া চলি আছে all right so you think about this now again, visualize properly. All right, so one atom is actually shared by 8 unit cells. All right, so you can understand that, right? This one is actually 1/8 of a atom. So you think about this, if I had another unit cell here, this would have spread out like this, and this would have become 1/4, right? 2 unit cell will make 1/4, another 1/4 this side, another 1/4 on the top, another 1/4 on the other side behind. So that finally adds up to 1/8 of an atom. So inside this unit cell, this atom is 1/8 the part of a full atom. All right, and how many of these are there? 1, 2, 3, 4, 5, 6, 7, and 8, right? In the 8 corners. So you will have 8 1/8 part of atoms there, 1/8 parts. So we will say total number of atoms inside the unit cell will be 8 times, because they are at the 8 corners, and one corner has 1/8 of an atom. So finally we say that there is one atom in volume actually. It's like parts taken out from 8 atoms, but once added up together, the volume, it is equivalent to 1 atom inside the unit cell. Okay, so for a simple cubic structure, we have 1 atom inside the unit cell. All right, now regarding the coordination number here, we are saying it is 6. All right, that means if you look here, it has one, this is if you talk about this particular atom. All right, so it has 1 atom here, nearby 2 here, 3 here. Now if we build up the crystal, you'll see we'll have another one here, another one to the top, and another one this side coming out of the screen, right? So we will have 6 of them nearby, which are bonded to 1 atom. So 1 atom will have 6 bonds in a simple cubic structure. Okay, so this is a very, very simple structure. Not too many crystals are available actually that follows the simple cubic one, but it is always wonderful to discuss this because it is a very basic one, and it makes understanding or comprehension easy. Okay, now these are a few more unit structures. So unit cells, sorry. So this is the one we discussed already, the simple cubic. If you look at it, it's something like this. This is a densely packed one, and this is showing the unit cell dimension, okay, and the form. Okay, this is a simple cube. It's a cube, and we have one each at the 8 corners. That is a simple cubic structure. Now, if we have something like this, where there are one each at the 8 corners and one at the center of the cube, like this here, you see, one is at the center of the cube, then we call it as a body-centered cubic. Okay, we call it as a body because this is inside the body of the lattice, all right, the crystal lattice. So unit cell, it's inside the unit cell, so it's called a body center. Now we have put it as blue here because it means that normally this can be the same atom or a different atom, but typically these are always the same ones. All right, that means if we say, I'm just giving an example. If I say zinc oxide, okay, but this is not a zinc oxide crystal, okay, it is not a body centered. Zinc oxide is not body centered. But if I say if this is zinc oxide, then suppose these four and these, the red ones are zinc and the blue one is oxygen. Okay, so I'm saying that no, this can happen, but this can be also zinc, right? So if it is an elemental thing with a BCC crystal structure, then it will be all same here. But if it is some salts, right, that have two elements in it, some composite materials, then this can have a different atom sitting at the center. So this is called as a body-centered cubic crystal structure. This one is another form of a cubic structure, which is called, where you see what is happening here is that the corner atoms are there, like the simple cubic one, and you have one atom on each face of the unit cell. Each face, okay, it is sitting on the face. So there are 6 faces in a crystal, and that's why there are 6 of those atoms sitting there. Okay, it's very difficult to visualize, but you can understand this is one plane, right? This is one plane. All these red ones are sitting at the corner, and this blue one is sitting in the center of the face. Previously here it was in the center of the body only, that's why only one. Here it's the center of the face, and there are 6 faces, so there are 6 atoms. So this type of crystal structure is called face-centered cubic crystal structure. Okay, so this is body-centered cubic, simple cubic, body-centered cubic, and face-centered cubic. So I hope you can visualize this one. Just hold on. Oh, is it? Uh, uh, ঠিক আছে দিয়া, let me pick this up here to see how it can be done. সেইটো কম্পাৰ্টমেণ্টেলো হৈ গ'ল নেকি? Okay, okay. আচ্ছা ঠিক আছে, we'll handle this. মই ক্লাছটো লৈ লৈছো ৰবা, I'll call you later. All right, so hope this is clear. Okay, let's go to the next one. This is just showing, you know, if we take one atom and we look at the number of connections, this basically tries to explain the coordination number, right? 3, 4, 6. See? So coordination number for this one is 6. Right? All these are the 6 atoms that is closely connected to it. Right? That means there is a bond. If there is no bond like this one, it will be considered for the calculation of the coordination number. All right. Now, this is a representation of a body-centered cubic, right? Now, you can see this one. It's easier to understand now. I already showed you before for a simple cubic where all these atoms are touching each other. Now, since there is an atom sitting inside, these corner atoms cannot actually touch each other, but they were put forcefully in. That's why, the amount of volume occupied by these atoms now is different from the previous case of a simple cubic one. So if you look here now, again, these are 1/8 the part of a atom, right? Because there are 8 unit cells nearby. I think I can show you better here with the previous figure. So you see here, if I consider this as one unit cell, then this is the next unit cell. All right, this is above it, this is at the corner. So you think about this one now. Already you see it is being shared by this one, this one, this one, and this one. And if you come this side, there are another 4 sitting here, right? So it's easier to take this one. So you consider this one, you see one unit cell here, one here, one here, and one here. That's 4. And above also 1, 2, 3, 4. Right? That is sharing this one. So that's a total of 8, right? So here also, this is atoms at the corner, so shared between 8 atoms. That's why this is 1/8 of an atom, right? So if you're asked how many atoms are there inside a body-centered cubic, then it will be 8 of this 1/8. So 8 into 1/8 will give you 1, and there is 1 sitting inside. So the total number of atoms inside a BCC is 1 plus 1, which is 2, right? So 2 atoms per unit cell, 1 in the center, and the same 8 found in the simple cube at each corner of the will give you. So this is 1 and this is 1. This will come out to be 2. And the coordination number, so it means the number of adjacent atoms, is 8 here. All right. The age length calculation will come to that later. Packing fraction also will come to that later. Let's first understand it. So it's clear to you now from this figure, right, that there are 8 corner atoms, and since they are divided between 8 unit cells, so in one unit cell we have 1/8 of an atom. So 1/8 of an atom, we have 8 of them, so 1/8 into 8 gives you 1, and there is 1 inside, that makes it 2. All right, so this is for the body-centered cubic. This is the face-centered cubic now. So if you look here now, the corner ones are there already. These corner ones are there. All right, these are the corner ones again. So it will be again 8 of them, and it is 1/8 because each one is divided between 8 unit cells, and there are 6 on the 6 faces. All right. Now, if you think about a face, how many unit cells are sharing one face? It is just 2, right? Because if I go back again, if you consider these 2 unit cells, I mean this particular face inside, like this is one unit cell, all right, going right up to here, and this is the other one. Now if I place an atom on this wall here, it will be shared only between these 2 unit cells, right? Unlike these atoms which are shared between 8 unit cells. Okay, so if it's a face, then it will be shared only between 2 unit cells, and that's why this particular atom on the face, half of it will be inside the unit cell and the other half will be in the other unit cell, right? So that means apart from 8 corner atoms, there are 6 face atoms. So the 8 corner atoms is divided between 8 unit cells. So it is 1/8, right? So that's why it is 1/8 here into 8 corner atoms. That will give you 1. And there are 6 faces, and each face has cut an atom into half, right? So half is inside the unit cell, so 6 into half, all right? So that will give you 3 plus 1 equal to 4. So in a face-centered cubic crystal structure, The total number of atoms inside one unit cell is 4. Okay, so that's how we do the calculation. So obviously now the amount of what we call as a packing fraction, that means the amount of mass inside a unit cell as compared to the total I will say the volume of space occupied by atoms to the total volume of the unit cell is what we call as the atomic packing factor, or AFP. All right, some also call it as atomic packing fraction. All right, it basically means the same. Some express it as a ratio, some express it as a percentage. Okay, anything is okay. All right, so this is what we are trying to explain. See, this is like a corner atom, right? So this corner atom is divided between 8 unit cells. All right, 8 of them. You see there are 8 unit cells. This is 1 unit cells, 2, 3, 4, and 5, 6, 7, and 8 behind. And this is the face. So if you see the face can be shared by only 2 unit cells, and that's why we take half of it. All right, I hope this is clear. So this is just to explain again. All right, these are the half atoms, all right, and these are the 1/8 atoms, and we sort of calculate how the 4 atoms actually come, 1 from the corners, 8 corners, 1/8 each, and 3 from the faces, 6 faces, half each. Right, so that's how we do the calculation. So coming to the packing fraction I was talking about, right, that means the volume of the, or rather the space you can say, or the volume occupied by atoms inside a unit cell to the total volume of the unit cell is what is called as the packing fraction, or when you express it as a packing efficiency, then we simply express it as a percentage. All right, it's basically what we are talking about, the packing fraction. So packing efficiency for a body-centered cubic cell is about 68%. That means for a body-centered cubic unit cell, about 68% of the total volume of the unit cell is occupied by atoms. For a typical simple cubic structure, where there are only the corner atoms, then it comes to 52.4% if it tightly, forcefully put it in. This is one, right? This is the simple cubic, and sorry, this is the body-centered cubic. There's one inside, and this is the simple cubic. All right. So for simple cubic, you see the amount of, or the volume that is occupied is lesser than that of the body-centered. And for the face-centered, it will be even more. The packing efficiency will be about 74%, right? So these are some complex structures. So we call as a hexagonally closed packed structure, or this is a face-centered cubic structure. All right. So I will not discuss this at the moment. We'll come to that later. But this is slightly complex crystal structure. Okay. Let's now try to calculate the atomic packing factor. Right? We already said, it's about 52%. That's what I said, right? 52.4%. So how does this calculation actually come in? All right. Let's try to do the simple calculation. So now if I consider this side of the cube as suppose A, all right, let me see if I can this one. All right, so let's say this side is oh sorry, I need to pick up first. Okay, let me go to the pen. All right, so yeah, let's say the side is A. All right, we said all the 6 sides are A, and let's assume that this radius of these atoms, considering them as spherical atoms, if we say the radius from here to here is suppose r, right? So two values we are taking, A and R. Okay, so now you look here, how much is R now. You see that 2 times R, because this is A, right? The side is A. From here to here it is A. So 2 times of R is A, right? That we can observe that twice R is equal to A. There's no doubt on that, right? Any side you look, this is A and this is R. So R plus R is A, right? Now we have 8 of those atoms. So if I now have to talk about the volume of the unit cell, if I say volume of the unit cell, let me write as C. Volume of the cell is what? This is a cube, right? So it's A into A into A. So this will be A cube, right? So this will be A cube. Now we have to find out the volume inside that is occupied by atoms, all right? So what will be the volume of a typical sphere, because the atoms are spheres? So if I say a volume of one atom, if I am to find out one atom, all right? Now we already know the radius, it is R, and the volume of a sphere is what? 4 by, I hope you remember, 4 by 3 pi R cube, right? So it's 4 by 3 pi R cube. And here, of course, if I have to compare with the volume of the cell, which is in as a function of the side A, so here we will pull in the A now. So it's 4 by 3 pi. R is now how much? A by 2, right? R is A by 2 cube, right? So this will give you 4 by 3, sorry, 4 by 3 pi A cube, right? Pi A cube by 8, right? 2 cube is 8. So if I have to cancel that out now, 4 will cancel out 8 as 2. So you are getting what? A cube by 6. Is it okay? So now we are saying the packing fraction, right? The packing fraction will be the volume occupied by the atoms. All right. So this is the volume of one atom. So the fraction inside is how much? 1 by 8 of this one. All right. So we already know that it is one atom inside, correct? So either you can write it like this, that 1 by 8 of A cube by 6, that is the volume occupied by one fraction of the corner, and there are 8 corners. Like we say, it's just one atom, right? So that's, we can directly plug it in. If we say into 8, then 8 will cancel out, right? Divided by the volume of the unit cell. So we get 8 cancels out, of course. So we have A cube cancels out. So we will have 1 by 6, right? Is it okay, or did I make a mistake somewhere? By 6, just a minute. 4 by 3 pi r cube is the volume of one atom. 4 by 3, A by 2 is r, so A cube by 8. This is 2, this is 6. So how much does it come out to be then? Wait, I think I made a mistake. Where did I make a mistake? Can anybody tell me if I made a mistake somewhere? It's 4 by 3 pi r cube. That looks okay. Because we need it to be 0.52, right? Thus, I mean, 4 by 3 pi r is a by 2. That's 8 a cube. All right. So let me check. I should have the answer here. So this is a cube. That's what we did, right? 4 by 3 pi r cube by a cube, right? So then if you calculate it out, it comes out to be 0.52. All right. Yeah. So that is the value. 0.52 you see there. That is the answer. And this is how we do the calculation. This is one atom inside the unit cell, 24 by 3 pi r cube. That's what I did, right? One atom, because we cancelled this 8, so it's 4 by 3 pi r cube and divided by a cube. Right? 4 by 3 pi r cube divided by a cube. Right? That's what we do the calculation, and the answer for the simple cubic structure, it comes out to be 0.52. Okay. Now we try for a BCC. So BCC comes out to be, I think, 64% or something we said before. So how do we calculate that now? So here you see again, all you have to do is, here now there are two atoms, right? There are two atoms, we already know, one atom from the corner coming in and one atom inside. There are two atoms. But how do you calculate the value of R now as a function of A? Because this is A now, right? And this is R. So this time twice R is not A because there's a space here, right? This is the space because of the presence of the central one. We cannot actually force these atoms more inside. Okay. So if this is R now, this is R. So it cannot be, A cannot be twice R. So how do you calculate now? So you have to see how the atoms are touching each other. Now, if I have to do a calculation as a geometric function, then I'll have problem if I consider these two, all right, because this one is touching, but this one is also touching. So I have to consider corner atoms now. Suppose if I consider from this corner to that corner, you see, if I consider this corner to that corner, then what will happen? I have one R from this one touching through this, going through the center of the center one, right? So that will be 2R here and 1R here. All right, that means this distance from this corner to that corner is actually equal to 4R, R plus R plus R plus R. All right, and so if we can find out this length, then we know. So if I'm at the moment, suppose I'm calling this length as X, all right, it came out as plus, whatever. So if I call it as that one, then this is equal to 4R, right? You all agree? This is equal to 4R. R plus twice R for this one, because it's completely going through. R plus twice R is 3R plus another R, that's 4R. Okay. But how do you find out this value now? So you see here, we will use Pythagoras theorem there now. So ultimately, what we'll do is, if you look at that one, then if I can pull his line from there to there, think about it. This is a right angle triangle. All right. That means it is going like this, from this point to that point to this point, right? So if you see here, this is a right angle triangle. Now we know this one as A, right? So how much is this one now? From Pythagoras theorem, if you see that is A, then this is A, then we say in a right angle, this is right angle, right? This is the right angle. So if I consider this triangle now, then it is, what do you say, this side. Now if I call it as something else, say suppose I call it as y, all right, then y will be what? Actually y square will be equal to a square, right, plus a square, correct? A square plus a square will be y square from Pythagoras theorem, right? Similarly, now if I consider this one, now this is the right angle now for this triangle, right? This is the right angle and this side is a, correct? So we need this side now. So that was what is this one, right? So if I say this is that one, then this one square will, sorry, this is square, huh? Square will be equal to this square, a square, plus this square, right? This square. So this is y, so this is y square and y square. So if I say this is as y square, then y square is equal to twice a square, right? A square plus a square. So if I say this as twice a square, if I use that as just a minute, twice a square, then this will be now equal to a square plus twice a square, which will be equal to 3a square, right? So what will be this distance now? What do I call it, x or plus whatever? What will be the distance now? This was square before, so I'll say this is equal to square root of 3a square, which will be root 3a, correct? So this distance here, this distance is root 3a, and we already said that distance is equal to 4r, correct? So meeting is ending in 5 minutes, so immediately please join back. I'll continue for another 15 minutes maybe, and then we will wind up. All right, so you see here now, that means now we can say that root 3a is equal to 4r, right? And we need the value of r as a function of a. All right, so r is equal to root 3 by 4a. Is this clear to everyone? So this r that we are talking about, previously for the simple cubic it was simply a by 2, but for the body centered cubic it is root 3 by 4a. All right, so now if you want to do the calculation for the fraction, we already said error. So if we, r is the radius of the atom, so the volume of the atom is 4 by 3 pi r cube. So if we plug in the value of r, this is 4 by 3 pi. We plug in the value of r, it's root 3 by 4a cube. All right, so you calculate that out now. Sorry about this phone, keeps on ringing too much. Just hold on. Just hold on a second. Hello. Morning. Yes. Oh, মানৱ মই ক্লাছ এটা লৈ আছো, মই কল বেক কৰো তোমাক ক্লাছটো হৈ গলে, হা? All right, so this is clear now. That means this will be 4 by 3 pi 3 root 3 by 4 cube, all right, into a cube. All right, so that is the volume. You can always cancel out. Okay, this 3 will cancel out, this 3 will cancel out with this 3, this 4 will cancel out one of these, so we'll have 4 square here, so that will be 4 square now. So we will have root 3 pi by 16 a cube. All right. Now, once we have this value, we can simply plug that in, and we can now for the packing fraction, you have volume of the atom, right? And there are two atoms now inside, correct? For a BCC, there are two atoms, so 2 into the volume of the atom and divided by the volume of the unit cell, which is a cube. All right. So if you plug in this value, you are supposed to get, I think, about 0.74 or something. You do this calculation, but I have already done it for you. So that's how it goes. If you plug in those values, you are supposed to get 0.68. All right. So that is the answer. 0, 0.68. You need to do this, okay? You plug in these values. If you plug these values here, VA, you are supposed to get 0.68. You do this calculation and try it out, okay? So this is for a body centered cubic. All right. Now we need to next try out for the FCC. So now for the FCC, we already know